Imagine traveling faster than the speed of sound, the ground a blur, the sky a violent, howling void. And then, in a single heartbeat, you have to leave the aircraft. No countdown, no second chances, just a handle, a prayer, and the most violent ride a human body can survive. What happens next is a story of physics, pain, engineering genius, and the razor-thin line between life and death that military pilots walk every single time they strap into a supersonic jet. Today, we are going inside that moment, the most dangerous fraction of a second in aviation history, and we are not going to hold anything back. Before we go any further, let me give you one number: 768 miles per hour. That is the speed of sound at sea level. Now imagine hitting a wall of air at that speed with your human body. No cockpit around you, no windshield, just you, a seat, and the raw, unfiltered fury of supersonic wind. Scientists call the force involved in that impact a dynamic pressure load. The pilots who survived it call it something else entirely, and most of them are still searching for the right words decades later. This is not just a story about technology. This is a story about the men and women who flew machines that pushed beyond every known limit of human endurance, about the engineers who stayed up for weeks trying to figure out how to save a life in half a second, and about the moments in history where everything went wrong, and somehow, impossibly, somebody survived. We are going to talk about the physics of supersonic ejection, the anatomy of what happens to a human body when it leaves an aircraft at Mach 1 and beyond, the evolution of ejection seats from crude explosive catapults to the most sophisticated life-saving devices ever built, and the real stories of pilots who pulled that handle and lived to describe what they felt. So settle in. This is going to take a while, and every single minute of it is going to change the way you think about the people who fly the fastest machines ever built by human hands. Let us go back to the very beginning. The year is 1942. The Second World War is raging across Europe, and German engineers working for the Heinkel Aircraft Company are staring at a problem that nobody has ever had to solve before. Their new jet-powered aircraft, the Heinkel He-280, is flying faster than any propeller-driven plane ever built. And the engineers realize something terrifying. If a pilot needs to get out of this aircraft in an emergency, the traditional method of simply climbing out of the cockpit is no longer possible. At the speeds these jets are flying, the moment a pilot tries to stand up and bail out, the airflow will slam them back into the tail of the aircraft with lethal force. They need a new solution. They need it fast. And so, almost out of desperation, they invent the ejection seat. The first ejection was performed on January 13, 1942, by a test pilot named Helmut Schenk. His aircraft had its controls freeze in icy conditions, and he became the first human being in recorded history to use a compressed air ejection seat to escape a doomed aircraft. He survived, and in that survival, a new era of aviation safety was born. But here is the thing. Schenk's aircraft was not traveling at supersonic speeds. It was not even close. The ejection seat that saved his life was essentially a very powerful seat that launched him out of the cockpit so the airflow would carry him clear of the aircraft. It was violent. It was crude. But it worked, and it worked because the speeds involved, while fast, were still within a range that a human body could physically tolerate. The problem, the real, terrifying, deeply complicated problem, came later. It came when aircraft started breaking the sound barrier. It came when the jets got faster and faster and faster still. It came when engineers started building aircraft that routinely flew at Mach 2, Mach 3, and beyond. And suddenly, the question stopped being simply how do we get the pilot out of the aircraft, and became something far more complex. How do we get the pilot out of the aircraft at supersonic speed without killing them in the process? To understand why this is so difficult, you need to understand what supersonic speed actually means for a human body. Let us start with something called dynamic pressure. Dynamic pressure is the pressure that a moving fluid, in this case, air, exerts on an object moving through it. And here is the critical thing about dynamic pressure. It does not increase linearly with speed. It increases with the square of velocity. What that means in practical terms is this. If you double your speed, you do not double the dynamic pressure your body experiences. You quadruple it. If you triple your speed, the dynamic pressure on your body is 9 times greater. The relationship between speed and the forces involved is brutal and unforgiving, and it scales in a way that makes supersonic ejection categorically different from subsonic ejection. Not harder, not more dangerous. Different in kind, not just in degree. At subsonic speeds, let us say below about 400 miles per hour, the forces involved in an ejection, while violent and capable of causing injury, are survivable without extraordinary protection. The pilot might suffer compression fractures in the spine from the explosive charge of the seat. They might have wind blast injuries to exposed skin and eyes. But the body, fundamentally, can endure the experience and remain functional. The limbs stay attached. The organs stay where they belong. The pilot hits the wind and, with luck, ends up dangling from a parachute, battered and shaken but alive. At supersonic speeds, none of those assumptions hold. At Mach 1, 768 miles per hour at sea level, the dynamic pressure on an unprotected human body is measured in thousands of pounds per square foot. At Mach 2, it quadruples. At Mach 3, it is 9 times the Mach 1 value. To put that in terms a human body understands, consider this. At Mach 1 plus, the wind force hitting your outstretched arm would be sufficient to tear it from its socket. The force hitting your face would flatten your features, force air into your sinuses and lungs at pressures they were never designed to handle, and potentially rupture your eardrums, your eyes, and the soft tissues of your throat in the first fraction of a second. The human body, which is a magnificent and resilient machine in most circumstances, is simply not built to exist in a supersonic airstream. It is not even close to built for it. We are soft and warm and held together with connective tissue, and supersonic air does not care about any of that. And then there is the deceleration. When a pilot ejects at supersonic speed, they go from Mach 1 or Mach 2 or whatever velocity the aircraft was traveling to 0 in a distance measured in feet and a time measured in fractions of a second. The deceleration forces involved are measured in g, multiples of the force of gravity. At 15 g, most untrained humans will lose consciousness. At 25 g, the forces are sufficient to cause internal organ damage. At the kind of instantaneous deceleration spikes associated with supersonic ejection, the numbers climb into ranges where the human body begins to fail structurally. Bones break, blood vessels rupture, organs shift violently inside the body cavity. The brain, suspended in cerebrospinal fluid inside the skull, slams against the interior of the cranium with forces that cause traumatic brain injury. And all of this happens before the parachute even opens. Now let us talk about a moment in history that crystallized all of these dangers into a single, unforgettable event. The year is 1955. The United States Air Force is testing the North American F-100 Super Sabre, one of the first production aircraft capable of supersonic flight. A pilot named George Smith is flying an F-100 when the aircraft goes into an uncontrollable dive. Smith, facing certain death as the aircraft plunges toward the ocean, pulls his ejection handle at an altitude of approximately 6,000 feet. His airspeed at the moment of ejection is approximately Mach 1.05, just barely past the speed of sound, but past it nonetheless. What happens next is documented in meticulous detail because George Smith survived, and his survival was so improbable and so medically significant that the Air Force and medical community spent years studying exactly what his body went through. The deceleration Smith experienced upon ejection was measured at approximately 40 g. His body was subjected to a wind blast so severe that his flight suit was shredded. The oxygen mask was torn from his face. His shoes were ripped from his feet. The centrifugal forces during the ejection sequence caused severe internal bleeding in his sinuses and abdomen. His vision was destroyed temporarily by the pressure wave. He was unconscious before his parachute opened, and he hit the water still unconscious, where he was recovered by a nearby boat. George Smith spent months in the hospital. He suffered liver damage, damage to his sinuses, damage to his hearing, and various other internal injuries. But he lived, and his survival, against every statistical and physical expectation, became the foundation on which engineers built a new generation of ejection seat technology. Because here is the thing about aviation engineers. When they see someone survive the impossible, they do not celebrate and move on. They ask why. They ask exactly what happened, in what sequence, at what force levels, and they take that information and they use it to design systems that transform the merely survivable into the reliably survivable. George Smith's ejection was survivable by accident, by the specific combination of his physical conditioning, the angle and direction of his ejection, the proximity of rescue, and a significant measure of pure luck. The engineers who studied his case set out to make supersonic ejection survivable by design. And that project, that decades-long effort, produced some of the most sophisticated engineering achievements in the history of aviation. The modern ejection seat is a machine of staggering complexity. Let us walk through what happens in the first second of an ejection, a second that contains more engineering precision and life-saving technology per millisecond than almost any other device ever built. The moment a pilot pulls the ejection handle, a sequence is initiated that is partly explosive, partly mechanical, and entirely choreographed to give the human body the best possible chance of survival. In aircraft with 2 crew members, the sequence is coordinated so that both seats fire in the correct order to prevent the second ejection from passing through the fireball of the first. The canopy is either blown off by explosive bolts or punched through by a special spike on the top of the seat. In the milliseconds between canopy departure and seat firing, small rockets called thrusters push the seat along rails inside the cockpit, orienting it for the most favorable exit trajectory. Then the main rocket motor fires. The rocket motor in a modern ejection seat is not a single explosive charge. It is a precisely calibrated propulsion system designed to accelerate the seat and pilot out of the cockpit at a rate that clears the aircraft's tail, which is, itself, moving through space at the aircraft's flight speed, while keeping the instantaneous acceleration below the threshold that causes spinal compression fractures. The target acceleration for most modern seats is between 14 and 22 g, sustained for a fraction of a second. Getting this precisely right is an engineering challenge of the highest order, because too little thrust and the seat does not clear the tail, and the pilot dies. Too much thrust, and the spinal column collapses, and the pilot dies. The margin between these outcomes is measured in milliseconds and fractions of AG. Once clear of the aircraft, the seat's attitude control system, which may use small gyroscopes, accelerometers, and miniature rocket thrusters, works to stabilize the seat and pilot in a position that minimizes the dynamic pressure loading on the body. This is critical at supersonic speeds. An ejection seat tumbling uncontrolled through a Mach 1.5 airstream will subject the pilot to forces that vary wildly and unpredictably with each rotation. Forces that will tear equipment from the body, cause severe injury, and potentially kill. A stabilized seat, by contrast, presents a consistent aerodynamic profile to the airstream, and the engineers can design that profile to manage the loads on the human body within survivable limits. The stabilization systems in modern seats are remarkable. Some use a small drogue parachute, A miniature chute deployed almost immediately after ejection to both stabilize the seat and begin decelerating it. Others use telescoping booms or fins that deploy to create aerodynamic stability. The most sophisticated seats use inertial measurement systems and active thrust vectoring to maintain attitude control throughout the ejection envelope. These are not simple devices. These are precision aerospace engineering achievements that happen to be attached to a chair. At supersonic speeds, the deceleration from maximum velocity to main parachute deployment speed must be managed carefully. If the main parachute opens at supersonic speeds, the forces involved would destroy the parachute, the harness, and the pilot in that order. Modern seats use a barometric sensor and an airspeed sensor to determine the optimal moment for main parachute deployment, ensuring that the pilot has decelerated to a safe opening speed before the chute unfurls. This sounds simple. It is not. At high altitude, where supersonic aircraft routinely operate, the air is thin and the terminal velocity is much higher than at sea level. The pilot might be descending at speeds that would be fatal for parachute opening for many thousands of feet before the air becomes dense enough for the chute to open safely. The seat must keep the pilot alive and stable throughout this entire descent. And then there is the question of altitude. Supersonic military aircraft routinely fly above 60,000 feet, altitudes where the atmosphere is so thin that an unprotected human being would lose consciousness within seconds and die within minutes from hypoxia and the explosive decompression of bodily fluids into near vacuum. Modern ejection seats carry their own oxygen supply, sufficient to sustain the pilot throughout the ejection sequence and descent. They also carry an automatic oxygen switching system that connects the pilot to the seat's supply the instant the aircraft's supply is disconnected. In the chaos and violence of a supersonic ejection, the pilot does not have the manual dexterity or the cognitive function to make these switches manually. The system must do it automatically, correctly, and instantly. Let us now talk about the specific aircraft that pushed ejection seat technology to its absolute limits. The aircraft that made engineers confront the hardest possible versions of all these problems simultaneously. The Lockheed State Route 71 Blackbird. If you know anything about aviation history, you know the name. If you do not, here is what you need to understand. The State Route 71 was the fastest air-breathing aircraft ever built. It flew at speeds exceeding Mach 3.2, more than 3 times the speed of sound, at altitudes above 80,000 feet. At Mach 3.2 and 80,000 feet, the skin of the aircraft reached temperatures exceeding 500 degrees Fahrenheit from aerodynamic heating alone. The aircraft was not just fast. It was operating in a regime that was, by any reasonable measure, incompatible with human survival outside the cockpit. The ejection seat designed for the State Route 71, the Lockheed State Route 71 encapsulated seat, or more accurately, the SR-71's specially designed David Clark full-pressure suits combined with the Lockheed-built seat system, was unlike anything that had come before. Because at Mach 3.2, there is simply no way to design a conventional open ejection seat that will keep a human being alive. The dynamic pressure at that speed is so enormous, and the aerodynamic heating is so intense, that an exposed human body would be killed almost instantly by a combination of mechanical forces and thermal injury. The air itself would be hot enough to cause burns. The pressure would be sufficient to cause catastrophic injuries. There was no conventional solution. The answer was encapsulation. The State Route 71 pilot wore a full-pressure suit, essentially a personal spacesuit, and the ejection seat was designed to keep the pilot enclosed and protected throughout the ejection sequence. The suit provided pressure, oxygen, and a degree of thermal protection. The seat provided stabilization, deceleration management, and parachute deployment. Together, They created a cocoon around the pilot that was theoretically capable of keeping them alive even at the extreme speeds and altitudes of the SR-71's operational envelope. I say theoretically because no State Route 71 pilot ever actually had to use the ejection system at Mach 3.2 and 80,000 feet. The system was tested. It was validated through extensive analysis and lower speed testing. But the full operational scenario, maximum speed, maximum altitude ejection, remained, thankfully, a scenario that existed only in engineering documents and computer simulations. There were State Route 71 ejections. In the history of the program, 12 State Route 71 aircraft were lost to accidents, and some of those losses involved crew ejections. But the ejections that occurred happened at lower speeds and altitudes than the aircraft's maximum performance envelope, at speeds where the ejection system, extraordinary as it was not being tested to its absolute design limits. The engineers who designed that system spent years working on a problem that, in its worst-case form, never had to be solved in reality. And perhaps that is the best possible outcome. That the greatest feat of ejection seat engineering ever attempted remained a solution to a problem that never needed solving in the most extreme terms. But other aircraft pushed the envelope in ways that did produce real ejections at extreme conditions. The McDonnell Douglas F-4 Phantom II, a workhorse of Vietnam-era air combat, was capable of speeds exceeding Mach 2, and F-4 pilots ejected at high speeds on multiple occasions throughout the aircraft's service life. The F-4 used the Martin Baker Mark V and Mark VII ejection seats, and while these seats performed well by the standards of their era, ejections at high Mach numbers in the F-4 produced a grim catalog of injuries. Shoulder dislocations were so common at high-speed ejections that they became almost expected. Spinal compression fractures were routine. The wind blast environment at Mach 1.5 or above was severe enough that limbs could flail to the point of dislocation if they were not properly positioned at the moment of ejection, which, in the chaos of a real emergency, they often were not. One of the most significant developments in ejection seat history came as a direct result of studying these high-speed injuries. Engineers at Martin Baker and at the United States Air Force developed arm and leg restraints, systems that would automatically pull the pilot's limbs into a safe, controlled position at the moment of ejection before the seat left the aircraft. These restraints were not a comfort measure. They were an engineering solution to a specific, documented, lethal problem. Without arm restraint, a pilot ejecting at high speed might have their arms swept back by wind blast with enough force to dislocate the shoulder or fracture the humerus. With arm restraint, the arm is held in a position where the forces are distributed safely. The difference between these two outcomes might be the difference between a pilot who is functional enough to manage their parachute descent and a pilot who is injured and incapacitated, descending into hostile territory or open ocean unable to signal for rescue. Let us talk about the physiological effects of high-speed ejection in more detail, because this is where the story gets deeply, viscerally human. The human spine is a marvel of biological engineering, a flexible column of bones and cartilage and ligaments that allows us to walk, run, twist, and bend while protecting the spinal cord that carries signals between our brain and the rest of our body. But the spine was designed for the forces of normal human activity. It was not designed for the forces of ejection. The compressive force of an ejection seat rocket firing is delivered from below, transmitted up through the seat, through the pelvis, and up the spinal column. If this force exceeds the compressive strength of the vertebral bodies, the blocky bones that stack to form the spine, those vertebral bodies will fracture. Spinal compression fractures in ejection seats are so common that they have their own classification systems and treatment protocols in military medicine. Studies of ejection seat accidents across multiple air forces have found spinal injuries in a significant percentage of ejections. Estimates range from 20 to 40% of all ejections resulting in some degree of spinal injury, with the rate increasing significantly at higher ejection speeds and altitudes. Most of these injuries involve the thoracic and lumbar spine, the mid-back and lower back, where the compressive forces are greatest. Many of these injuries are survivable and even recoverable with appropriate treatment, but some result in permanent neurological deficit, paralysis, loss of sensation, chronic pain that follows the pilot for the rest of their life. The ejection seat saved their life, but the price of that survival was paid by their spine. Engineers have attacked this problem from multiple angles. The seat design itself has been refined to minimize the peak compressive force while still providing sufficient thrust to clear the aircraft. Seat cushions and harness systems have been designed to distribute force across a greater area of the body, reducing the peak pressure at any single point. And pilot training has been modified to teach the optimal body position for ejection: back straight, head back against the headrest, arms inside the cockpit rails, feet on the footrests, a position that aligns the spine along its strongest axis and minimizes the leverage that can amplify compressive forces into fractures. But there is another category of injury that supersonic ejection introduces that subsonic ejection does not: thermal injury. At Mach 2 and above, the air itself heats as it compresses against a moving surface. This is the same phenomenon that heats the leading edges of a supersonic aircraft to hundreds of degrees, aerodynamic heating. When a pilot ejects into a Mach 2 airstream, the air around them is not at ambient temperature. It is heated by compression to temperatures that can cause burns to exposed skin in seconds. At Mach 3 and above, the heating is severe enough that unprotected skin would be burned almost instantly, and even the aircraft's structural materials require special heat-resistant alloys to survive the thermal environment. This is one of the primary reasons that the highest performance aircraft require pressure suits. The suit provides not just pressure and oxygen, but thermal protection from the aerodynamic heating environment of extreme speed ejection. Now let us talk about the engineering evolution that took the ejection seat from the crude compressed air catapults of World War II to the sophisticated life-saving systems that protect pilots today. The story is one of continuous iteration, driven by accident investigation, combat experience, and the relentless application of engineering ingenuity to what is fundamentally a constraint optimization problem. Maximize the probability of pilot survival subject to the constraint that the solution must fit inside the cockpit of a fighter aircraft and operate correctly on the first try, every time. In the worst possible circumstances, Martin Baker Aircraft Company, founded by James Martin and Valentine Baker in England in the 1930s, became the world's preeminent ejection seat manufacturer through a combination of engineering excellence and sheer stubbornness. Martin, a brilliant and difficult man who ran his company with obsessive attention to detail, treated every ejection seat failure as a personal failure and every successful ejection as a validation of principles he had developed through years of painstaking work. The Martin Baker seat went through dozens of marks, versions, each incorporating lessons learned from accidents, tests, and the growing body of knowledge about human tolerance to ejection forces. Today, Martin Baker ejection seats have saved more than 7,500 lives. That number, 7,500 human beings who would otherwise have died, is the measure of what engineering applied to the problem of human survival can achieve. The American side of the ejection seat story runs through companies like Weber Aircraft, McDonnell Douglas, and most recently UTC Aerospace Systems, which produces the ACES, Advanced Concept Ejection Seat, used in most United States Air Force aircraft today. The ACES seat represents the current state of the art in ejection seat technology. It uses a computerized sequencer, essentially a dedicated computer, to manage the ejection sequence with a level of precision and adaptability that earlier mechanical and pyrotechnic systems could never achieve. The ACES sequencer reads the aircraft's flight condition at the moment of ejection, speed, altitude, attitude, and adjusts the ejection sequence parameters in real time to optimize survival probability for the specific conditions encountered. At low speed and low altitude, the seat fires with maximum thrust to gain the altitude needed for parachute deployment. At high speed, the seat fires with carefully modulated thrust and deploys stabilization and deceleration systems in an optimized sequence designed to manage the wind blast environment. The seat, in effect, adapts to the emergency rather than executing a fixed program regardless of conditions. This adaptability is the key advance that separates modern ejection seats from their predecessors. Earlier seats were designed with fixed sequences: fire, stabilize, deploy drogue, deploy main chute, executed at fixed intervals regardless of the actual flight conditions at the moment of ejection. This meant that the seat was optimized for an average ejection scenario, and ejections that differed significantly from the average, whether in speed, altitude, or aircraft attitude, were less well served. A seat designed to deploy its main parachute after a fixed time delay might deploy that parachute at dangerously high speed in a high-altitude ejection, or might deploy it too late to allow full inflation before ground impact in a low-altitude ejection. The adaptive sequencer eliminates this problem by making the deployment decisions based on actual real-time data rather than predetermined timing. Let us now turn to some of the most remarkable and instructive ejection stories in aviation history. The cases that push the boundaries of what survival looks like and what the limits of human and engineering endurance really are. We have already talked about George Smith in 1955. Let us talk about some of the others. In 1966, a United States Air Force pilot named Joseph Kittinger, who was already famous for his 1960 record-setting parachute jump from a balloon at over 100,000 feet, was shot down over North Vietnam in an F-105 Thunderchief. He ejected at high speed and subsonic altitude, survived the ejection, and spent nearly 8 years as a prisoner of war. Kittinger's story is not primarily about the ejection itself. It is about what came after. But his ejection and survival under combat conditions illustrates one of the key realities of military ejection. The ejection is only the beginning of the survival challenge. Once out of the aircraft, a pilot in a combat zone faces all the hazards of the ejection itself, plus the hazard of capture, evasion, and the entire brutal calculus of being a downed aviator behind enemy lines. In 1969, during the development testing of the North American XB-70 Valkyrie, a massive experimental aircraft designed to fly at Mach 3, not an ejection story per se, but one of the most dramatic aircraft accidents in American history. The XB-70 was involved in a mid-air collision during a photo shoot, and the two aircraft that collided went down, taking 2 pilots with them. The surviving crew member from the XB-70, Al White, was saved by his encapsulated ejection seat, a seat that enclosed the pilot completely in a protective capsule before ejecting. White survived with serious injuries, but the incident underlined both the life-saving potential of encapsulated seats and the terrible cost of when those systems fail or are unavailable. It was also a reminder of how fast things can go wrong at high speed and how little time, fractions of a second, separates survival from death. The stories from the Vietnam War era provide perhaps the richest body of real-world ejection data in history. Hundreds of American pilots were shot down over Vietnam and North Vietnam, many of them ejecting at high speeds and varying altitudes. The medical data from these cases drove significant improvements in ejection seat design, pilot equipment, and rescue procedures in the decades that followed. One of the consistent findings from Vietnam-era ejections was the high rate of spinal injury. a finding that pushed Martin-Baker and American seat manufacturers to accelerate their work on reducing peak spinal loads. Another finding was the critical importance of limb restraint, as many pilots suffered severe arm and leg injuries when their limbs flailed in the wind blast of high-speed ejection. During the Gulf War in 1991 and the subsequent decades of air operations in the Middle East, ejection data continued to accumulate. Coalition pilots flew combat missions in conditions that ranged from low-altitude high-speed strikes, where ejection at transonic speeds over the desert was a real possibility, to high-altitude bombing missions where the threat was surface-to-air missiles capable of destroying an aircraft in milliseconds. The ejection seats carried by these pilots, Martin-Baker Mk-10 and Mk-16 in British aircraft, Aces-2 in American aircraft, represented the then-current state of the art, and they performed accordingly. Survival rates for ejections in the Gulf War era were significantly higher than they had been in Vietnam, reflecting both improvements in seat technology and improvements in rescue procedures and equipment. Let us talk about a phenomenon that often gets overlooked in discussions of ejection seats: the psychological aftermath of ejection. The physical injuries of ejection are well documented and extensively studied, but the psychological impact of a supersonic ejection is less often discussed, and it is profound. Imagine the experience from the pilot's perspective. One moment you are in the cockpit of a sophisticated aircraft, in control of your environment, surrounded by familiar instruments and procedures. The next moment, in less time than it takes to complete a single heartbeat, you are outside the aircraft, exposed to a wind that is trying to destroy you, with no control over what happens next. The violence of the ejection itself, the explosion of the rocket motor, the blur of acceleration, the shattering impact of the wind blast, is experienced as pure, overwhelming sensory assault. Many pilots report partial or complete amnesia for the ejection itself, with memory resuming sometime during parachute descent or even after water or ground impact. The period after ejection is described by survivors in remarkably consistent terms: a profound, disorienting silence after the noise of the aircraft and the ejection sequence, the sudden awareness of open sky and falling, the relief or terror depending on whether the parachute opens correctly, and then the long, swinging descent. Time to think about what just happened, time to prepare for landing, time to assess injuries, time to begin functioning as a survivor rather than a victim. Many pilots have described this period as one of the clearest moments of their lives, a period of intense sensory awareness and focused thinking that stands in contrast to the complete sensory overload of the ejection itself. Post-traumatic stress after ejection is common and underreported. Military culture has historically been resistant to acknowledgement of psychological injury, and many pilots who experienced severe ejections minimized or concealed their psychological symptoms in order to continue flying. The long-term study of these populations has revealed significant rates of PTSD, anxiety disorders, and depression, consequences that are less visible than a spinal fracture but no less real, and no less a product of the experience of supersonic ejection. Let us now discuss the current state of ejection seat technology and where it is heading. The ejection seats in service today, the Martin-Baker Mk-16, the Aces-5 in American service, are extraordinarily capable devices. They operate reliably across an enormous envelope of speeds, altitudes, and aircraft attitudes. Their computerized sequencers manage the ejection process with a precision that was simply impossible in earlier eras. Their survival equipment, the oxygen systems, the radio beacons, the life rafts, and survival gear packed into the seat survival kit, give a successfully ejected pilot a genuinely good chance of rescue even in remote or hostile environments. The modern ejection seat is, in every meaningful sense, a triumph of engineering applied to one of the hardest problems in aviation safety. But the future presents new challenges. The emergence of hypersonic aircraft, vehicles capable of sustained flight at Mach 5 and above, will push ejection seat technology into territory that even current systems cannot handle. At Mach 5, the dynamic pressure and aerodynamic heating are so extreme that conventional ejection is simply not viable. The thermal environment alone, with aerodynamic heating producing temperatures that approach those of a blowtorch, would kill an unprotected pilot in milliseconds. Encapsulated ejection systems, like those designed for the State Route 71 but taken to a new level of sophistication, are likely to be the only viable solution for hypersonic escape systems. These systems will need to manage thermal loads, dynamic pressure loads, and deceleration forces in an environment more hostile than anything current technology has faced. There is also the question of unmanned systems. As military aviation increasingly incorporates unmanned aerial vehicles, drones, the question arises of how much effort should be invested in developing escape systems for manned aircraft when the trajectory of military aviation seems to be moving towards systems that do not require human pilots. The answer, for the foreseeable future, is that manned aircraft will continue to fly combat missions alongside unmanned systems, and the pilots in those manned aircraft will continue to need the protection of reliable, capable ejection systems. The investment in ejection seat technology is an investment in the people who fly the most dangerous aircraft ever built, and as long as those people are flying, that investment will continue. Let us zoom out now and think about what the story of supersonic ejection tells us about something larger, about the relationship between human beings and the machines they build to push the limits of what is possible. Every time aviation engineers have created an aircraft that flies faster, higher, or in more extreme conditions than anything before, they have been confronted with the same fundamental question: how do we protect the human being inside when everything goes wrong? And the answer to that question has always required the same combination of ingredients: deep scientific understanding of the limits of human physiology, rigorous engineering analysis of the forces and environments involved, relentless testing and iteration, and a willingness to accept that some problems require solutions that have never been built before. The ejection seat is, in many ways, a monument to the value that military aviation places on the people who fly its aircraft. The cost of developing, manufacturing, and maintaining a modern ejection seat is enormous. A single modern seat can cost hundreds of thousands of dollars. The weight and volume that the seat occupies in the cockpit could, theoretically, be used for additional fuel or weapons. The engineering resources devoted to ejection seat development could be directed toward other aircraft systems. But the decision, made and reaffirmed across decades and generations of military aviation, has been that the life of a trained military pilot has a value that justifies this investment. Not just a human value, though that is central to it, but a practical, operational value. Training a military pilot to the level of skill required to fly a supersonic jet is a multi-year, multi-million-dollar process. Losing that pilot in an accident that could have been prevented by a better ejection system is not just a human tragedy. It is a significant operational loss. The numbers make the case clearly. Martin Baker alone has saved more than 7,500 lives over the history of their ejection seat program. If you estimate the cost of training each of those pilots at something in the range of $1 to $5 million, a conservative estimate for modern military pilot training, the value of those saved lives in pure operational terms is measured in the billions. And that calculation does not include the value of the human lives themselves, which are not reducible to dollars and cents, but are nonetheless the ultimate justification for every dollar and every hour invested in making ejection safer. There is one more story I want to tell before we bring this to its conclusion. It is the story of a young British test pilot named John Fifield, who in 1958 became one of the first people to eject at truly high speed. In his case, from a de Havilland aircraft traveling at approximately Mach 1, and who survived to provide investigators with a detailed and coherent account of his experience. What makes Fifield's account remarkable is not just that he survived, but the precision with which he was able to describe, in the calm aftermath, exactly what he had experienced in those fractions of a second. He described the initial violence of the ejection, the impact of the wind blast, the tumbling of the seat before stabilization, the deployment of the parachute, the long descent. His account became a foundational document for researchers trying to understand not just the physics of high-speed ejection, but the human experience of it. What a person perceives, what they feel, what they remember. What Fifield described was not a heroic experience. It was an overwhelming one. The forces involved were so far beyond anything in normal human experience that the mind struggled to process them even as they were occurring. The violence of it was total, not pain exactly, but something beyond pain, a force that simply exceeded the categories of sensation that normal life provides. And yet, Fifield said, there was a quality to the experience that was not entirely negative. The moment he was clear of the aircraft and the parachute had opened, there was a quality of absolute stillness, a silence so profound after the noise and violence of the ejection that it felt, in his words, like a kind of peace. That moment, the sudden stillness, the parachute overhead, the sky around you, the ground far below, is the payoff for everything the engineers have built into the ejection system. Every calculation, every test, every iteration of the seat design, every improvement to the harness and the drogue and the barometric sensors and the oxygen system, all of it exists to create that moment. The moment when the pilot is clear of the stricken aircraft, alive and descending with a chance to survive. Not a guarantee, not a certainty, but a chance that would not exist without the engineering, the testing, and the human ingenuity that went into building a machine that can take a human being from supersonic flight to a hanging parachute in less than 2 seconds without killing them. The next time you see a military jet streaking across the sky, a silver needle at altitude, trailing a thin white condensation trail, think about the seat inside that cockpit. Think about the engineering that went into it, the years of testing and refinement, the lives it has saved, and the lives it is ready to save. Think about the pilot sitting in it, trusting that if the worst happens, that seat will do what it was designed to do. And think about George Smith, tumbling through the sky at Mach 1.05, conscious and then not conscious, his aircraft gone and his parachute not yet open, in the middle of the most violent and improbable survival event in the history of aviation to that point. He lived. Against the odds, against the physics, against every reasonable expectation, he lived. And because he lived, engineers learned. And because they learned, the next pilot who had to pull that handle had a better chance. And the one after that. And the one after that. 7,500 times over. That learning translated into survival. 7,500 people who came home to their families, who walked out of hospitals, who flew again, or retired, or became engineers themselves and designed better seats for the next generation of pilots who would push the next generation of aircraft beyond the limits of what anyone had thought possible. That is the story of supersonic ejection. It is a story about physics and physiology and engineering genius. But underneath all of that, it is a story about the extraordinary lengths that human beings will go to in order to give other human beings a fighting chance to survive. And that, perhaps more than any technical detail, is what makes it one of the most remarkable stories in the history of flight. Thank you for spending this time with me exploring this extraordinary chapter in aviation history. If you found this journey through the science, the engineering, and the human stories behind supersonic ejection as fascinating as I did. Please leave a comment below telling me which part affected you the most. Was it the physics? The survival stories? The engineering? The medical reality? I read every single comment, and your thoughts genuinely shape what we explore next. And if you are new here, welcome. This channel is dedicated to the stories that military and aviation history does not always tell loudly enough, and there is much more to come. Hit subscribe and the notification bell so you do not miss what comes next.